Welcome everyone. This is our usual winter school every year, and this year we have the great pleasure to have Huy Tuan Pham from Institute of Advanced Study. So Huy got his PhD from Stanford fairly recently, but already he's like a superstar in our area, and did some groundbreaking work in extremal, probabilistic, and additive combinatorics. So we this time he will tell us his breakthrough work on this probabilistic combinatorics related to threshold phenomenon. So yes, it's all yours.
Thanks everyone for coming, and thanks Hong for the invitation to give the mini course. So roughly the plan for this week will the week will break up roughly into two parts. So in the first part, we will discuss more of the conceptual developments. So we will build bridges that connect various different quantities connected to thresholds of general properties. And most of what we discuss in the first half will take place in very general context, as you will soon see. And then towards the later half of the week, we will focus on more combinatorial applications. So we will look at specific nice combinatorial applications and see how we can apply what we developed in the first half to these specific problems. And there we will see a lot more of the familiar elements in extremal and classical combinatorics. So that's the rough plan. So to start everything, let's discuss one of the at least main motivating setups for our discussion, and which I'm sure many of you are familiar with. So it's just the Edishmani in the graph. And as usual, we'll denote an Edishmani random graph by G and P. And this will simply be a graph or a random graph on n vertices. And for every pair of vertices among these n vertices, we are going to flip an independent coin. This coin is a Bernoulli P coin, so it is going to give a 1 with probability P and give a 0 with probability 1 minus P. And if the coin turns out to be a 1, then we add an edge connecting the corresponding two vertices. Right? So every pair of vertices will be connected independently with probability P. This is a very simple model, and at the same time very ubiquitous. And for us, at least for a majority of the discussion in this mini course, we will be interested in properties of sparse Edishmani random graphs. So we should think about P as a function of n that goes to 0 as n tends to infinity. And many times the interesting function might be decaying like a polynomial in 1 over n, maybe 1 over n, 1 over root n. So think about P as being in that range of parameters. Okay, so what is our motivating question? What do we want to understand about these random graphs? For each large value of n, we can, for instance, fix some graph H on n vertices. And in many cases, this graph H could be just a fixed graph that doesn't use all of the n vertices, like a triangle. It could also be the case that H is a large graph that uses this growing n number of vertices. For example, it could be a Hamiltonian cycle, which means a cycle that goes through each of the n vertices exactly once. And here we allow in this general question any graph H that we can put now on n vertices. And we ask, okay, what is the probability that this random graph G and P contains H as a subgraph? And later on in the week, we will also see various generalization of this setup, but let me mention these as we get to that. So for now, as I mentioned, because in the first half, we will be working with the conceptual development, and sometimes it is useful to look already beyond this specific context of the random graph. So let me actually just tell you about this general setup that encapsulates this specific class of motivating example. So in the general setup, all that we are given is some finite set, finite domain, X. Now the randomness is going to be on subsets of X. So we will define XP as a random subset of X. Where each single element of X is included in this random subset independently with probability P. If at any point there's any confusion with my abbreviation or anything is not clear, please immediately interrupt me. Okay, so just to see that the context of the Eddy-Shreni random graph is an immediate special case of this general setup, you can take, for instance, X to be the set of all pairs of vertices among a given ground set of n vertices. And in this case, XP will have exactly the distribution of an Eddy-Shreni random graph G and P. Now, in this general context, for this type of property that we were going for in the random graph, turns out that the correct generalization of it is, well, the one easy property that we can see for this property is that it is monotone, right? If I give you a graph that contains H as a subgraph, and if I add more edges into this graph, then any new graph that I form will always contain H as a subgraph, because containment as a subgraph is a monotone property under H addition. And that is kind of the main information that we will remember in this general setup. So we will be interested in monotone properties. And for us, now, the property will be over subsets of X, right? So these now replace the role of the random graph in the motivating example. Okay, so what does this mean? Formally, you can just think about this monotone property P over subsets of X as a collection of subsets of X with the property that if you have a subset S that satisfies this property P, and you take some superset T of S, then P must also satisfy this property P. So P is a property of subsets of X that cannot be destroyed by adding more elements. Okay, so again, for example, P, which is described by all graphs containing some H as a subgraph, would be monotone. Okay, so in that context, let me actually write in a more convenient form what general monotone properties look like. So the claim, which is very simple, is that for any monotone property P, let me first set up some notations. Okay, let me set it up here. So for a given set S inside X, subset subset of X, let me write bracket S for the upset generated by S. So this is simply all of the subsets of X that contains S as a subset. Okay. And let me now, for a family of subsets of X, curly H, let me denote bracket of curly H. The family, you can write it as the union over all of the sets in this family, the upset generated by that set, or in other words, it's all of the subsets of X such that W contain at least one H from this family. Okay. So again, for instance, in this example of, well, yeah, just to be explicit, in the case of the random graph, so the ground set is pair of vertices, and this property P, okay, and if I take, for instance, H, the collection of all copies of the graph H on this ground set of n vertices, then this upset of H, this exactly just describes all the graphs on n vertices containing H as a subgraph. So for this monotone property that we wrote down here, we can equivalently describe it in terms of this upset generated by the family curly H, where the family curly H is exactly the family of copies, isomorphic copies of the graph H. And in general, for any monotone property P, can be written in this form. For some family of subsets of X, curly H. And of course, you can see vice versa, that any family given by bracket H for some family of subsets of X will automatically be monotone. So this is an equivalent description of any monotone property. And let me quickly note, just to avoid confusion, that this family script H doesn't have to be monotone, right? So for example, here, the family of all copies of H is clearly not monotone. Okay, so far, not much has happened. Okay, so now let's state the general question that we are interested in. So for given monotone property P, or you can equivalently write it in this form, bracket H, when does XP, so a random subset of X for each element is included with probability P, or if you wish, you can also most of the time just think about this as a uniformly random subset of X with density exactly P. And for most results, they will carry to both of the setups. So we ask, when does XP likely satisfy this property P? So we ask, for which parameter P should we expect that the random subset XP would typically satisfy the property of interest P? Another way that you can think about this is that you have a family of structures that you care about. So in this case, for example, the copies of the graph H are the nice structures that you are going for, and you are looking at when your random graph will likely contain at least one of these desired structures. So at least one of the desired copies of H. Okay, so with this, let me make another easy observation. be in the form of a plot. So for any monotone property P, equivalently described as bracket H, if we plot the probability for this curve is the probability that xp satisfies the property P, and this is viewed as a function of the density parameter P for the random subset, then we can observe that the function which maps the density P to this probability will always be continuous and increasing. And in fact, you can easily see that it will increase from 0 when P is equal to 0 to 1 when P is equal to 1. Well, except for small caveat, which is the trivial case where this property P or the family of sets generated by curly H is just either the empty set or the entire collection of subsets of X, in which case this kind of function has trivial behavior. So let's ignore these degenerate cases. But otherwise, it has this nice continuous increasing property. And so in particular, because it increases from 0 to 1, there will always be actually a unique point along this curve where this value is exactly equal to 1/2. So I want to declare that that is a special value for me, right? Because it is exactly the transition point at which when we sample a random subset with density below that parameter, then the random subset xp will unlikely satisfy the property that I care about. So it's satisfied with probability strictly less than half. And if we sample the random subset with density above that parameter, then it will likely satisfy the property that we care about. So let's give that a special name. This is actually our definition for the threshold of P, or by this point, equivalently, you can think about this as the threshold of the family of structures H is defined, and we'll denote this PC of H is the value P between 0 and 1 such that this probability is exactly equal to 1. And well, there are other notions of threshold, actually more coerced, that have been previously introduced, for example, in extremal combinatorics and in the previous study of random graphs. But this specific way of pinning down exactly this threshold corresponding to this probability 1/2 is kind of a more precise way to capture many of these notions. So let us just work mainly with this notion of the threshold of this increasing general monotone property. So, any questions so far?
But increasing was strictly increasing.
Oh, so right. So here in this context, if we are avoiding these two degenerate cases, then increasing here will actually mean strictly increasing. Okay. So now let's get to the first calculation that we will do. And we will start again from the very basic. So just the first mode. So one way that So first I will define some notations to kind of rewrite the kind of properties that we are interested in over here in kind of more convenient notation. For a subset for W of X, let's define the following function. N curly H of W. And this will simply be the number of sets in the family script H that is a subset of W. Okay. In other words, you are interested in sets that contain at least one of the desired structures or sets, which are the ones that are staying in this family curly H. And for general W, NH of W is simply counting how many of these desired sets your specific set W is containing. Okay. So, of course, in this language, we can describe curly H simply as the collection of all subsets W of X, where N curly H of W is at least one. So this probability that the random subset XP is containing one of the desired structures, this is the probability that N curly H of W is at least one, the probability of this specific event. And now you can see that we can put here this rather trivial bound. We just replace that probability that this random variable is at least one by the expected value of the same random variable. So one way that you can think about this is just, well, all that we are doing is really, well, we have here kind of the expectation of a rather complicated, nonlinear, and annoying random variable that is the indicator that this nice random variable NH of W is at least one. And this indicator is fairly annoying. But anyway, because NH of W always take a natural number value, so it's either 0 or above 1. This function, the indicator that NH of W is at least 1, is always upper bounded, is always dominated by exactly this same random variable, NH of W. So that's one way that we have simplified our situation. We just strip away this complicated indicator. And we'll see later that we will fight really hard to be able to put this back, because in some sense, this is in the end what we really care about. And another way that you can think about this is that, well, this is nothing more than a naive union bound, right? So here I am asking for the probability that, oh, sorry, why did I put here? XP should be everywhere. Here I'm asking for the probability that the random set XP contains at least one of the sets from the family H. And of course, that's by the union bound is at most the sum of the probability that XP contains each specific set in this family curly H. And by linearity of expectation, you can actually see that that is exactly the same as the expected value of this random variable NH of XP. Okay, and well, yeah, actually just said the magic word, but what did we gain when going through this upper bound is that exactly because this function NH has this nice summation form in terms of these much simpler events, and by linearity of expectation, we can now explicitly evaluate this expectation. Just the sum over H from our family script H, P to the side. Okay, so now what have we achieved? Well, on this right-hand side is something that we can, at least for every value of P, and whenever we are given a specific family script H, we can just do the calculation and evaluate what this is. And the current claim, okay, so let's give that quantity on the right-hand side a name because it will appear many times. So let me call it CP of script H, simply the sum H over script H, P to the side the set H, in other words, just the expected value of this random variable. Now, what we observe from this upper bound is that whenever we go in, explicitly evaluate this quantity Cp of H, and we observe that this is small, let's say smaller than 1/2, then immediately we can conclude that this probability that we care about is at most 1/2. And if you look back at the definition of the threshold PC of H, this is just equivalent to the claim that the true threshold PC of H is at least this specific parameter P that we did the calculation here. Okay, so if you want to find a lower bound to the threshold, it's going to be, at least if this works, an easy task. Well, for a second, what you can first try is just sit down and try to evaluate CP of H, see if that is indeed small, and if it's small, you immediately get a lower bound to the threshold PC of H. So let's see perhaps one quick example of how this works in action. Okay, so yeah, so this section is the first moment. So let me just say that still nothing much has to go on, but I will call this, already give this a name. So I will call this phenomenon here. So this Cp of H being smaller than 1/2. This is a first moment obstruction. So it's an obstruction to your random set XP containing your desired structures from the family script H. And I will put here an additional adjective. It's a naive obstruction, and we'll see how to make it less naive in a second. So let's do one example. Okay, so let's start from a simple one. So for these examples, I will almost always stick to the motivated setup of the random graph. So X is n choose 2. And in the first example, the family of graphs that we care about, script H, is just the family of all copies of the clique on 4 vertices on n vertices. Okay, so this is a clique on 4 vertices. Okay, so, well, given this very simple family, of course, we can very quickly evaluate Cp of H. We want to show a quick answer. Very homogeneous.
Don't be shy.
Don't be shy. Yeah, right. Of course, we can be more careful, but yeah, we'll soon see that I will not even try to be careful. So yeah, here you can write, for example, n choose n to the 4, p to the 6. Very good bound, and will work for almost anything that we will do later on. If you want it exactly, it's n choose 4 times p to the 6. There are 6 edges in every of these graphs. Okay, one thing that you have to be careful is when translating between the set theoretic setup and the random graph setting, the size of the set would always translate to the number of edges, right? So our random variable in the random graph are on the edges. So we'll always be counting edges. And so all of these are p to the 6, and then the number of K4s we have in this family curly H, the number of ways to choose 4 vertices out of n is n choose 4. Anyway, it's some constant times n to the 4, p to the 6. So this is smaller than 1/2, in fact, very small. If, let's say, p is smaller than some little constant times n to the negative 2/3. Okay, so as we saw from above, the threshold will have to be at least lower bounded by order n to the negative 2. Okay, so let's do a slightly more complicated example. Intermediate one. This one, just maybe for a little bit of a fun context, but because we have a talk on Friday, and anyway, one of the first application of the first moment method is really for this family of graphs. So A2 log n on n vertices. And again, you can quickly do your estimate of CP of this family. Going to be, well, doing what we do exactly over there for K4. I will save you some estimates actually, if this is log base 2, in exactly this parameter, this is going to work out to be a very small number. So order exponential and minus log n log n. So anyway, this is very small, much smaller than 1/2. Oh, sorry, what did I?
The CP.
Yes, I actually mean P equals to 1/2 because this was the application to Ramsey's theory. So, right. So this is actually just that very quick observation that you take Gn 1/2, then it doesn't have a click on 2 log n vertices. And the last example, let's just be a bit more general. So here, let's take any fixed graph H. And by fixed, I mean this graph H is not allowed to change with the number of vertices little n that we are sending to infinity. So H can be any graph that you can draw down. Drawing down this because I will later use it for a second. And this family H is again just the family of all isomorphic copies of H on n vertices. Okay, so well, of course we can still easily write down the naive, well, first moment obstruction or this naive quantity CP of H here. And it's not much different from before, right? So every of these graphs will have P to the number of edges in H. Sorry, each of them will have E of H many edges. And here we are going to take P to the number of edges. And then we are going to sum over all of the copies of H on n vertices. And the number of that is going to be of order n to the V of H, which is the number of vertices in the graph H. Okay, so let's keep this here for a second. At least what we immediately conclude from our easy discussion so far is that the threshold for this family will be at least n to the negative V of H over E of H. Okay. Okay, so with that, let's make one. Let's look at what we have so far. We have so far the very easy first moment argument, and out of it, all that we have been able to produce are lower bound to the threshold of any of the monotone property of this form. So as long as we can evaluate this simple quantity, check that it is small, we immediately get a lower bound to the threshold, PC of H. So the question that will be of main interest to us from now on to the end of the week is how do we put interesting upper bounds to this threshold PC of H? Or, well, so we have here a general way to produce lower bounds to PC of H. Are these close to being tight? Are there interesting behaviors that we may see? And let's first explore what can happen by doing kind of the very next thing that one would do in probabilistic combinatorics to try to put an upper bound on PC of H, which is the second moment method. Here. So, I mean, for upper bounding PC of H, what is our problem here, right? So we know, for example, that this first moment is very large. So on average, a random set would contain many copies of the desired structures that we aim to get from this family curly H. But in order to get a good upper bound on the threshold, our task is to show that for some good proper parameter P, we can actually guarantee that this random variable is at least one with a reasonably large probability. So we know that its average is large. And of course, that doesn't mean that the random variable is going to be non-zero with reasonably high probability, exactly because it can be dominated by a very small probability event under which event this random variable is extremely large. So somehow that pushes up the average significantly, but still the random variable is very small, or in fact zero for a majority of the time. That's what we don't want to happen. So in cases where the second moment method works, as we will see, we can rescue ourselves from this situation by saying that, well, if this random variable, nh of xp, is well concentrated near its expectation, then, well, if you have chosen a parameter p to at least ensure that the expectation is large, and if you can show that it concentrates, so for a majority of the time or a large fraction of the time, this random variable is staying close to the expectation, then of course, there's a large fraction of the times that you can guarantee that this random variable is staying away from zero. Okay, so that's the spirit of what we will quickly see now. And the second moment method we will very soon see will give us some general result, but it can only actually work in fairly restrictive settings. But before getting to its failure, let me tell you about at least some of the cases when it works. Okay, so again, the principle is if nh of xp concentrates around its expectation, and the expectation is large, then of course the probability that nh of xp is at least one will have to be large. And second moment method is one of the most classical way that you can at least try to show concentration of a random variable around its expectation. So what do we need for this to work? Well, we will need to compute the variance of the random variable that we are interested in. And if this variance is small, in particular, if this variance is, let's say, smaller than some little constant times the expected value of the same random variable, squared, then with reasonably large probability, so with probability 1 minus some other constant, you can be a lot more precise here, but I'm just stating what I need for our discussion. The random variable nh of xp is, let's say, at least half of its expectation. And let's say you have guaranteed that this expectation is large, in particular, much larger than 2. This is forced to be larger than 1. And you can make this constant c prime goes to 0 as you set this constant c also going to 0 appropriately. Okay, so in particular, we will now try to, in some cases, evaluate the variance of this random variable nh of xp, and then we'll see in which situation is it really literal of the square of the expectation. So for this, let's stick to this general example. So again, we have a fixed but general graph H, and our curly H is the family of all copies of H. Okay, so for this guy, the expectation was still in fact fairly easy to evaluate. Still, it's not so bad with the variance, but still already you will see that it's somewhat annoying to estimate. So let's try this calculation. Okay, so I'll start with some easy bound. Actually, you don't lose much by doing this. The variance of NH of XP. Anyway, that's the second moment subtracted by the first moment squared, right? Okay, now I will expand. Well, NH of XP is itself a sum over this simple indicator. So let me expand this expression in terms of this simple indicator. So for the second moment, what you will get is the following. So you will get different copies of the graph H on n vertices. Let's call it H prime and H prime prime. And you will get the expected value of the product of the two indicators. So the indicator that H prime is a subset of the random set X of the random graph XP, and the indicator that H prime prime is a subgraph of the random graph XP. And it turns out that, okay, let me write it in full first. And over here, well, you will just have the sum over H prime in H, and then you have the product of these, but we know what these are. So just P to the 2EH. Okay, but well, this indicator and the expectation is not so hard to figure out, right? So here, this is actually just the same as the indicator that the H union of these two copies, H prime, is a subgraph of the random graph XP.
The second summation over H.
So yeah, so I'm using H for this specific fixed graph. So think about H as like a triangle. And so E of H prime are anyway copies of H. So the number of H's in H prime are all the same as this number that is E of H. That's okay. So all right, so now let's continue from here. Well, the expected value that this indicator of the union of these two graphs is a subgraph of XP, that we know exactly what it is. So that is just P to the number of edges that we have in that union. Right? Okay, and maybe I'll write it this way. Okay. Now, well, most of the cases, well, if the two copies, H prime and H prime of H, are actually H disjoint, then the number of edges you have here would actually be exactly twice the number of edges of H. So this would just be 0. So all of these terms will then cancel. And then for the rest of the term, I will actually just forget about this because it will not contribute so much, this subtraction. So I will just bound it by the following term. So we'll look at all of the copies of H that have non-trivial intersection. And we sum P to the union of the H set of these two copies, but that's the same as P to the 2E of H minus the number of edges in the intersection of H prime and H prime prime. Okay. Right. So actually we have to do a bit of estimates for this calculation, but we are now quite close to the end. I'll just rewrite that summation over there in a slightly different way. Let me actually stay on this. So now I can rewrite it this way. So let me first sum over the first copy, H prime. There's actually this P to the E of H that never changes with the copy. So let's just put it out. Then, well, what is the constraint here? The second copy must intersect H prime in a subgraph of H prime that is non-empty, that have at least one edge, right? So instead of summing over H prime prime, I can sum first over a subgraph K of H prime, where the number of edges of K have to be at least 1. And then I will sum over the over all copies H prime prime of H that contains, so let me put here, that contains this subgraph K of H prime. And what will we sum in the end? Well, P to the minus the number of edges in the intersection. Here, let me put here then P to the minus number of edges of K. Okay, so here. Now you can think about what, okay, so this quantity, P to the minus E of K, it completely doesn't depend on, okay, so let's change the order a little bit here. Because P to the minus E of K doesn't depend on H prime prime, let's put it here. And here what we have left is the number of copies H prime prime of H that contains K as a subgraph. This one we can estimate quite easily, right? So for example, maybe this is H or H prime. This is K. Well, if we are going to now count how many copies of H are sitting on top of this subgraph K, K has 3 vertices and H has in total 5 vertices. So the number of these copies is, of course, at most n to the number of vertices in H minus the number of vertices that we already see in K. Right? So let me now put that upper bound in. And one final thing that you can observe is that if you take any copy H prime of H and you sum over the subgraph K inside H prime, you can actually just think about summing a subgraph K of H first without moving it according to H prime. And so that is a small change that I will put here for a second. So for the sake of time, let me be a little bit quick here. So let me fix one arbitrary copy of H on n vertices in advance. And now I'm summing over subgraph K of that specific copy with at least one edge. And then inside, I am summing oh, okay, let me not do that here for a second. Let's just stick with that. Might be easier to understand next time. Still, let's take H prime and then K a subgraph of H prime with at least one edge. And here we will have P to the minus EK and that upper bound that we have, n to the v of h minus v of k. Okay, so this, I claim, is now upper bounded by the following quantity. So this is upper bounded by p to the 2 e of h times n to the 2 v of h times the following quantity, maximum over all subgraph k of h with at least one edge of n to the minus vk, p to the minus ek. And then here I may put some constant depending on the graph. Okay, so to see this, I didn't do a lot. I just put here this n to the v of h out. So in here, I would have the quantity p to the minus e of k, n to the minus v of k. And if you call out this maximum, then any one of these terms, right, will be bounded above by this maximum. So in particular, now I have a sum here over the subgraph k of h prime with this one edge, but I can just repeatedly sum this maximum, and the number of times that I sum will anyway be bounded above by the number of possible subgraph of h prime, which is some constant that depends only on h, because h prime is a copy of h. Okay, once you do that, then all that you have left is p to the 2e of h, n to the v of h, some constant times this maximum, and then you have left the count or the sum over copies h prime of h of just the indicator 1, and that will give you another n to the v of h. So this is what you get in the end. Might be a bit of calculation, that's better that you look at it a bit more slowly afterward. But this looks like a pretty good shape for us. So we can just write this as some function depending on h, some constant depending on h, times this quantity here. Times really the expected value of the same random variable squared. We did compute the expected value before. I think I have erased it. It was on exactly the same board. So we go back to what we want, which is to have the variance being small compared to the square root of the expectation. Then all that we need to ask is for this quantity here to be small. Okay. And this will happen as long as this is small, or in other words, P is at least some constant times n to the minus minimum over subgraph k of h with at least one edge, v of k over e of k. Big constant. Okay, so almost the same shape as the lower bound on the threshold that we have from the naive first moment obstruction. So if you remember, the lower bound that we have, so this will imply, of course, the same, this will imply, of course, an upper bound on the threshold, PC of h. So PC of h is at most big O of this quantity here. And the naive lower bound we had before was PC of h is at least omega of n to the minus, well, we don't have the minimization. So before, for the lower bound, we only had n to the minus v of h over e of h. Okay. which one is the correct one? We guess. And can you easily see why the upper bound is the lower bound?
Find the subgraph from the original graph.
Great, thank you. So, right, indeed, at least, especially after we see the shape of the upper bound, it's very easy to see that it has to be the correct order, as you correctly observed. So, we can improve the lower bound from the naive consideration we had before. So indeed, so below this, the naive first moment of fraction, well, not for H, but for K, which is a subgraph of H, what tells us that XP typically does not contain K as a subgraph. But then, of course, because K is a subgraph of H, if the random graph doesn't contain K as a subgraph, then it also typically doesn't contain H as a subgraph. So that gives us the same lower bound for the threshold of the family of copies of H. Okay, so just, well, this is a nice conclusion for our exercise in calculating the variance. The threshold for this family of copies of the fixed graph H is always of order what we determine. Okay, and the one bonus observation that we had was that, well, in some cases, the naive first moment of fraction is way too naive. But it's not so hard, at least in this case, to see how to fix it. So now let's just generalize this fix to the general abstract setup that we have been discussing, right? General setup. Okay, so now I will introduce to you this notion of the expectation threshold, which is nothing much beyond the naive first moment of fraction with some fix to improve it, just like how we improve the lower bound for the threshold of this family script H right here. So let me make a definition that a bit mirrors what we have here. So given a family of set H in 2 to the X, we will say that a family of set G, also subsets of X, covers H if H is contained in bracket G, or in other words, every set in H contains some set in G. Okay, and the right feature you can imagine, but then maybe this is G, then the big ones are H. So if G covers H, is actually sitting inside H. And of course, the example, as we just saw, maybe H is a family of copies of some fixed graph H, and G is the family of copies of some subgraph K in H. This family G will obviously be a cover for the family H. Okay, so now let's continue the definition. Let's say that H is P small if there exists a cover G for H with this naive first moment obstruction. So this cost CP of G, the sum over set in the family G, P to the size of G, that this is smaller than 1. And now we'll define the expectation threshold. Let's make a very quick observation again. So whenever H is P small, then, well, CP of G is at most 1/2. So via the naive first moment obstruction that we discussed before, we conclude that the probability that a random subset contains one of the sets from G will have to be small. But if you want to contain a set from H, you must at least contain one set from G. So this immediately implies that the probability that XP is contained in bracket H also have to be small. And again, by definition, that is just saying that the threshold is lower bounded by this parameter. So whenever you have a cover with a small CP, that certifies a lower bound to the threshold of the family or the property that you are interested in. So now let me just make the convenient definition of the expectation threshold. Which we denote PE for expectation of H. This is simply the best lower bound that you can obtain this way. So this is, you can choose how you want to write it. I will write it in maybe the way that I prefer. So this is the smallest P such that H is not P small. Of course, there's nothing tricky with continuity here. So the other way that you can think about it is that it's the largest lower bound that you can obtain this way. So it's the largest P such that H is P small. So of course, go back to just the same example with the copies of H and the copies of the subgraph K of H. Then you can observe that the, right, so e.g. for H, copy of H, this family G, which is given by the copies of K, gives you a better lower bound. And because we actually, through the second moment method, determine the correct order for the threshold, we actually know that PE of this family H of copies of H have to be exactly equal to the order of the threshold that we determined before, which is n to the negative minimization over subgraph K of H, V of K over E of K. One example where we have determined both the expectation threshold and the threshold. Any questions so far? Okay. So also in this case, what we saw before is because we have the second moment method nicely working, we actually determined that the true threshold and the expectation threshold, the trivial lower bound, in a certain sense, they are on the same order. Okay, so now we could ask, yeah, is this true in general? Could we actually hope that this family of lower bound that we constructed by first, when we started from a naive expectation obstruction, a naive first moment obstruction, and then we may optimize over the cover, so we add some complexity for it. But the question is, does that always give us a good upper bound or determination of the correct threshold for the property that we are interested in? So, okay, so let's get a bit to that discussion. So let's just see one example where we are not confined to a family of structures that have a small bounded size as the number of vertices or the number of elements n grow to infinity. So let's now consider this example where H is a family of perfect matchings on n vertices. So first, let's think n is even. Okay, so, well, what is the first thing we can try? The naive first moment obstruction. We can compute CP of H. This is not so hard to explicitly evaluate. And it will look something like this. This is the number of perfect matchings on n vertices. And each of them have n over 2 edges. So we get this p to the n over 2. So in the end, this is going to be bounded by some constant times pn to the n over 2. So clearly, if you take p, a small constant dividing by n, then Cp of H is going to be very small. So in particular, you can immediately observe that the naive expectation obstruction already gives you this lower bound of order 1 over n. Okay, now you can actually do a little bit more. Well, before, when we have a graph H, sometimes we can pass to a subgraph and we can get a better lower bound. You can very easily check here that no matter which subgraph of the perfect matching, which is now just partial matchings, that you choose, and you compute the naive first moment obstruction for that, you won't get a better lower bound than 1 over n. And in fact, there's a very easy way to see that PA of H has to be of order at most 1 over n. Well, let's assume that somehow PA of H is not of order 1 over n. That means you can find some cover for the collection of perfect matchings that will have a small cost under this CP functional, where P is a big constant over n. So, well, if you want to have even a single perfect matching lying on one of the sets that you are using in the cover, so let's just take any cover G. We will return to this argument more formally in just a little bit, so I'll just briefly sketch you. We can take any cover G, and we can assume, without loss of generality, that G is just a collection of matchings. Because if it contains some set, some graph that is not a matching, then you can just throw it away without affecting anything. And now there's one kind of simple calculation that one can do. So for example, let's say there is some matching of size little g in this collection script G. We can count the number of perfect matching that extend this G matching Well, this we can actually write down explicitly, just the same as we write down the number here. So it's just what, n minus 2g factorial over 2 to the n over 2 minus g, n over 2 minus g factorial. So the same way that we count perfect matchings in a graph. Now we just have n minus 2g vertices left. So exactly the same formula here with n replaced by n minus 2g. And again, a simple calculation. Let me not do the estimates right here. This is going to be at most c over n to the g. Okay, so just from here, you can observe that if the c over n cost of the family g, so the sum over g, c over n to the size of g is small, then you cannot be a cover, because you cannot cover all perfect matching. The total number of perfect matchings that you can cover, so this is, okay, so this is multiplied by the total number of perfect matching. So in other words, each of the partial matching in your cover can only cover this specific c over n to the g fraction of the total number of perfect matchings that you have. So if the cost of the cover is small in this sense, then the total number of perfect matchings that you can cover, the total fraction of perfect matchings that you can cover is at most a half fraction of the entire space of perfect matchings. So that clearly tells you that this G cannot be a cover for the collection of perfect matchings. Okay, so just again, we'll revisit this argument a bit more formally in just a little bit. So this is at least just a quick way to see why P of H is of order 1 over n. So let's continue our observation a little bit. Now, we will turn to PC. And it turns out that there is an obstruction for containment of a perfect matching that feels to be having a little bit of a different nature from what the first moment or second moment can capture. Okay. So in fact, for any P that can be a lot larger than 1 over n, so in particular, we know in expectation, we must contain kind of anything that we wish. But if, as long as P is below some small constant times log n over n, then random graph G and P will contain many. And many means actually something like maybe, okay, n to the c or n to the 1 minus c, one of these, let's say n to the c, isolated vertices with high probability. But this is actually a simple calculation that you can verify with the second moment method. Let me not verify it right now, but you can show that if your probability P is below some constant, small constant times log n over n, then you will have this fairly big n to the c size subset of vertices for which there's no edge coming out of these vertices. But even if you have just one of them, of course, you cannot have a perfect matching. And in particular, this gives us another argument to show or to observe directly that the threshold for this family of perfect matching has to be at least of order log n over n. But in particular, it has to be separated away from the expectation threshold by a log n factor. And it turns out that, well, once you move to spanning structures like the perfect matchings, hypergraph perfect matchings, spanning trees, Hamiltonian cycles, or these general types of spanning structures, then in many, many cases, you will have an obstruction that is local, that is very much similar to these isolated vertices, obstructing the existence of the perfect matching. And in many of these cases, what will happen is that you will observe this separation of the threshold from the expectation threshold by this log factor. So we don't have a break today. Oh. Let's get to the punchline today. Okay, so I mentioned similar log n gap for many other spanning structure. That was one motivation for Kahn-Kalai. That's all I think. Yes. To pose the conjecture in the absolutely general context. So Kahn-Kalai proposed the following conjecture. In 2006, where actually determining the threshold of a lot of the interesting spanning structure, well, not the perfect matchings, turns out that, so for the perfect matching, we do know from quite remarkable proof of POSA in the 70s, 80s, that the true threshold is indeed of order log n over n. But exactly because of this log n factor gap, this has to be an interesting proof. This makes use of interesting combinatorial property in order to arrive at this bound on the threshold. We know that we can't really use first moment or some type of second moment method directly to arrive at this type of bound, even just for the family of perfect matching. And for many of the other more complicated spanning structures, where it's harder to get directly to them combinatorially, the determining the threshold is open, but the log n factor gaps is kind of the same for many of these examples. So Kahn-Kalai proposed that perhaps it's true in absolute generality that there is some universal constancy, again, does not depend on anything in the statement of the conjecture, such that, okay, let me state it first in this form. The threshold of any monotone property is bounded above by the expectation threshold. We may have this log factor, where log carries the cardinality of the ground set on which you are working. And of course, we have this trivial lower bound. So in other words, you can describe the conjecture this way. As long as you assume that you have a family script H of sets that is not piecemeal, being not piecemeal is the nice assumption, why I wanted to write the definition of the expectation threshold earlier this way. If H is not piecemeal, then if you sample a random subset of the domain X with probability C times P times log X, then it will contain one of the set from H with probability at least one. Okay, so this course would be powerful. So in any specific situation, it would imply directly the correct order for the threshold of several interesting properties. And okay, this next time I will give you the proof, but also after mentioning some further connections of this conjecture. So this is in joint work with Genome Park. Appears just last year. That this conjecture indeed this is true. And we will actually prove the following slightly more precise version. So the statement is if H is not P small, and let this parameter L be the maximum size of a set from this family script H, then X CP log L, again C is a universal constant, will contain at least one of the sets from H with high probability, with probability at least 1/2. Okay, so in particular, of course, the size of any set in H is at most X. So this is a stronger conclusion than what is asked for in the Kahn-Kalai conjecture. Also, for example, if you take H to be the family of all copies of this fixed size graph H, so all of the sets in H have a bounded size, then you see that we do not need any additional log factor. And it's true, we saw that the threshold actually matches with the expectation threshold in these cases. Okay, so we will prove this next time. I do have 5 minutes. So I will perhaps we just give here quick discussion of some of the at least immediate application, and we'll see more interesting application next time. So here are some of the immediate corollaries. And so, again, for historical context, one of the interesting cases is when you now take X, for example, to be and choose R. Think R is a fixed constant, like 3. And this corresponds, so XP would correspond to a random Edish-Renyi hypergraph, R uniform hypergraph. In this context, you can take the family H to be generalization of the perfect matching we look at in the graph case, so R uniform perfect matchings. And Shamir in the 80s asked to determine the threshold of this family of hypergraph perfect matchings. And even for 3 uniform hypergraph perfect matchings, they behave very differently from perfect matchings, right? So they are NP hard to find in general. And for exactly these reasons, we can't really get the direct way to find these hypergraph perfect matchings, and determining their threshold is hard as a result. But then, okay, so we do know from the remarkable proof of Johansson, Kahn, and Wu, 2008, that the threshold for D is of order log n times n to the 1 minus r. And let me say here that it is actually very easy to show that the expectation threshold is actually of order n to the minus 1 over r. Okay, why is this? Well, for the lower bound, you can just directly evaluate again CP of H. It's very easy to count the number of R uniform perfect matchings. And so you can easily get a lower bound on the expectation threshold of this order n to the 1 minus r. If you want to get the upper bound on the expectation threshold, again, I will say a little bit more next time about a general way to get at it. But we can use the same argument that we discussed before, because we can count these R uniform perfect matchings so easily. You can show that if a family script H cannot have a small cover because each single set in the cover can only cover a small fraction of the total number of R uniform perfect matchings. So if it has a small cost, you can show that they cannot add up to cover all of the perfect matchings that you need. That gives you a way to certify an upper bound. And in particular, the simple counting argument through the Kahn-Kalai conjecture would directly imply the correct order of the threshold of this family of order log n to the 1 minus r. And you can recover that result immediately. And then there are other type of spanning structures that you can look at. So for example, if you go back to the random graph setup, then a classical question is when this family H is the family of all copies of a fixed bounded degree spanning tree. And Kahn asked for the determination of the threshold of a fixed bounded degree spanning tree in the 90s. And this was resolved in the end by in a beautiful argument of Montgomery using the absorption method, fairly technical. And this is in 2019. He determines that the threshold for this family is of order theta of log n over n, where this depends on the maximum degree that you are looking at. And again, maybe I'll quickly say how next time the expectation threshold for this family is easy to determine. It is of order exactly 1 over n. And so if you want to get this order of log n over n, then again, the order for the threshold would follow immediately from the order for the expectation threshold. In both of these cases, why can you get the lower bound on the threshold of order log n to the 1 minus r here and log n over n here? In the case of the spanning tree, we already know the reason why, exactly just because of the isolated vertices. And in the case of the R uniform hypergraph perfect matching, roughly the same reason is why you need this log n factor here. So below log n times n to the 1 minus r, you will find vertices that have no hyperedge coming out of them. So you cannot find a perfect matching. Okay, so I think this is all of the time I have for today. So let's reconvene next time with a lot more connections and then the proof.
There's a question in the chat. The first question is, what about if the property is non-increasing? Do we still have notion of threshold, or is there an example of a non-increasing property with no threshold?
So once you start to look at non-increasing properties, then you could definitely easily write down properties that have no sensible definition of a threshold, because you could fluctuate. For example, if we look at the probability of containing certain graph H as an induced subgraph, then as the parameter when P is 0, this probability is 0, and when P is 1, this probability is also 0. But in between, you could have a point where there's positive chance that you get an induced copy of A. So there's no clear way of making sense of a notion of a threshold in these cases. Admittedly, there are many cases where the property is not strictly monotone, but for which you still roughly have this expected behavior that we saw when we draw the curve of that we defined the threshold before. But right, so but we say that if we want to make an absolutely general theory out of it, then it has to be quite tricky.
Why do you need a general upper bound for the durable constants? Do you have?
Yeah, so you can work to find the upper bound here. So for example, depending on the regime that we are interested in, so any case, because we will be mainly interested in large structures where this theorem is most applicable, if you send L to infinity, then this constant C can be made to be something very reasonable, like 3 to the 0.995. And that will come directly of the proof that we will see later, but it's reasonable constant.
Then if we can narrow down the bound for that universal constancy, then can we find us in some sense some sharp threshold for some several cases?
Yes, that's another interesting question. So, okay, so depending on the cases, sometimes, okay, so sharp threshold turns out have been studied and somewhat more understood from much earlier. So from the Boolean functional analysis and hypercontractivity in the 90s, and then lots of seminal results by Flickr, building on works of other people. We know general conditions that allow us to get sharp threshold. And in many cases, we can kind of, if you want to determine the sharp threshold or a specific point, we can do what we do here to determine at least roughly where the threshold is located. And then we apply abstract conditions that allow us to get sharp threshold. But right, it would also be interesting. I guess we don't have an example yet of really going along this technique and arrive directly at a sharp threshold. That I think might be interesting. But yeah, so far it has been a bit more separated, getting the location of the threshold and getting the sharpness of the threshold.
So you said if our family H is sort of constant size, then this your strengthening actually gives that we can forget about the log factor.
Yes.
Is there any other condition that also gives, like a general condition that gives this also for large structures? So
Yeah, so right, so we know some explicit, we can write down and next time I will introduce to you some explicit conditions stronger than this condition that we are assuming here of H being not P small that will allow us to remove this log L factor and that are useful in some of the combinatorial application. There are many, it is very interesting to just understand in general what is causing this log L factor to pop up, perhaps under this more general setup of a family being not P small. Of course, we know that log L cannot generally be removed if we are only making this assumption, but there are many interesting phenomena and many guesses at various tweaks that one can get. And in this case, if one expects to remove this log L factor, but there are lots of open questions on that end. But I will tell you at least one explicit condition next time that removes the log L.
Any other question? Okay, if not, let's thank Huy for a very nice